Mr. Bala sir is a technologist and a prominent thought leader in the IT industry with over 19 years of experience at Tata Consultancy Services TCS. He serves as a principal consultant and technology head for digital initiatives. Mr. Bala sir specializes in enterprise architecture, scalable and performance-driven architectures and innovative digital technologies. He is passionate about advancing initiatives in cloud computing, IoT, cognitive services, DevOps, data science, and analytics. In TCS, he plays a key role in mentoring and nurturing the technology community through coaching and leadership programs. Academically, Balasar holds master's degree in computer applications from the Osmania University, where he graduated as a university first rank holder. He is an Open Group Master IT Certified Architect and serves as a board member in the Open Group Certifying Authority. His extensive credentials include being the chairman of the IEEE Computer Society Hyderabad section, a founding board member of CMG India, and a managing committee member of the CSI Hyderabad chapter. He is also a member of Microsoft Visual Studio Insiders Club and recognized speaker at numerous prestigious conferences. He has delivered insightful talks on topics like cloud architecture, enterprise data governance, and digital transformation at global events. He has also authored several white papers, including contributions to Open Group publications and TCS perspectives on cloud computing. Balasar's commitment extends beyond professional achievements to fostering collaboration between industry and academia. He actively promotes learning and innovation, leveraging his deep expertise to align technological advancements with business goals. Thank you so much, sir, for accepting our invitation. Welcome to the session, sir. Sir, are you can you unmute yourself, sir?
Yeah. Can you see my screen? Please acknowledge. Yeah. Please acknowledge if you are able to see my screen.
Yes, sir. It is visible, sir.
Okay. Thank you. Thank you, Dr. Shilpa ma'am, and thank you, AV Energy, for inviting me for this wonderful faculty development program on quantum computing. This has been a very, very compelling technology which is going to shape the world in the future. As we are trying to understand about computing, quantum computing, you might have already witnessed a quantum chip was released by Google, which is called as Willow. How many of you are aware of that? Which is considered to be one of the most fastest computing chip available in the marketplace today. Willow has got an ability to solve the problems in few seconds or few minutes, which the traditional supercomputer would take septillion years. So you can understand how corporates have started investing in this particular technology. How important is this particular technology? While we try to speak so, it's very, very important for all of us to understand whether it is really worth that all the problems on the earth need to be solved with a quantum. Probably not. We need to be very, very choosy. We need to be very, very focused in selecting the problems which really requires a quantum as a technology to be leveraged to solve the problems. Probably during the course of this particular quantum computing things, you might have encountered some of the critical elements, taxonomy of quantum computing. I'm going to refresh on those particular things and also touch upon one of the important discussion piece, which is called as the integrating quantum machine learning with the classical systems. Some of you might be a data scientist, or some of the professors might be already having an artificial intelligence understanding and experience, and you're already educating a lot of students in that direction. So classical systems, classical machine learning, deep learning methods are aware to all of us. But how can we weave this quantum machine learning is something which is more interesting, and I believe everyone will be happy to understand this piece of an element to the great level. As part of this particular 90-minute talk, I'm going to touch upon the critical elements of the quantum computing and machine learning. and also touch upon some of the classical systems in machine learning, because this is important for all of us to get a connection established between the classical systems and the quantum machine learning. Then we'll deep dive into some of the concepts of the quantum machine learning and see how we can integrate quantum machine learning with the classical systems, and what are the use cases, what are the available frameworks available today which can help us in this entire journey. Hope that really resonates well with all of you. As I speak, so introduction to the quantum computing and machine learning. How many of you, I think you might have already gone through some of the constructs around this, but let me refresh some of the things for your reference so that we all understand what we are going to speak. So if you really take about the quantum mechanics, which is a fundamental branch of the physics, describes the nature at the smallest scales, such as atomic and subatomic levels, which underpins the quantum computing by introducing the concepts that classical systems cannot replicate today. Some of the key principles which I'm going to touch as I progressively move, you might be start seeing that or witnessing the facts that superposition is one of the most occurred piece as part of the quantum computing area. It's a quantum system which exists in multiple states simultaneously until measured. So basically, if you try to take a coin and flip it, people give this example very. Either it could be head or a tail, but when it is rotating in the air, that is the superposition state, what we try to call. Similarly, if you try to take the entanglement, so it's a phenomenon where qubits become interdependent such that the state of one qubit simultaneously affect the other, no matter the distance. So we heard about bits and bytes. Qubits is a nominal terminology under which the quantum computing measures the processing capability. And that's what you might have heard in the previous sessions as well. So two qubits can be in an entangled state most of the time. Measuring one qubit reveals the state of the other. So it's important that you understand this particular terminology and how it fits into the entire context of the discussion. The third important taxonomy element which you need to be aware of is the quantum gates. Quantum gates are the building blocks of quantum circuits manipulating qubits to perform computations. So basically, if you're trying to look into the quantum gates, there are three important quantum gates you might have seen or heard about. In case if there is a talk which has already been done in your discussions. The three gates which are very popular is a Hadamard gate, which is creating a superposition element. There is a control NOT gate, which entangles the qubits. And there is a third important gate called poly X gate, which flips the qubit state. So when you try to look into the Hadamard gate, as I mentioned about the coin toss, right, in quantum computing, when you try to apply to a qubit, it puts the qubit into a superposition state where it cannot be head or it cannot be tail. Till that it is rotating, it will be always in that particular state. So there is a mathematical representation given to that as well. And when you're trying to talk about the control NOT gate, that flips the state of the second qubit. So if and only if the first qubit is in triangle state or in entangled state. So it's about a classical conditional statement. If control is 1, then flip the target or else nothing. So poly X gate is a third important gate which you need to be aware. Basically, just when you're trying to look into the classical NOT gate, it flips the state of the qubit and becomes from 0 range to 1 and vice versa. Think of it as like a bit flip of a 180-degree rotation. That's how you try to look at it. The fourth important taxonomy in that circuit is qubits. Qubits are the fundamental units of the quantum information, which is very much analogous to the classical bits, but with quantum properties like superposition and entanglement, you see these things playing a very important role in the entire processing. That's where today when you try to go and procure any D-wave machines, which is the quantum machines, you look at a 2-qubit processing power, 4-qubit, 8-qubit, 16-qubit, 32-qubit. Likewise, you try to measure that. So having said that, just trying to go into the how quantum computing differs from the classical computing. This is very important for all of us to understand. So when you look into the different areas, the classical way of comparing the things, it all depends upon the way you try to represent the information. This becomes a very important element because in the classical world, you try to represent the information in 0 and 1, while in the qubits, you have 0 and 1 in the superposition states, which is a multiple states, what you try to look at. The second important difference, what you try to look in from the quantum to the classical computing is processing power. In the classical world, you process the data very, very sequentially in a very limited parallel threads, while in the quantum world, you process the data exponentially through a superposition and entanglement that really optimizes, that really pushes the speed at a scale under which it need to operate. The third important difference is in the logic and the algorithms under which it is trying to apply. So in the classical world, again, you try to be very, very deterministic algorithms. You expect certain things to happen that way. But in the quantum, it's all about the probabilistic methods. And the quantum algorithms, very, very popular algorithms, such as Grover's algorithm, Shor's algorithm, are leveraged in this entire journey. So Grover's algorithm is generally utilized as part of the search, while the Shor's algorithms is for the factorization methods you try to use. The data scaling is a fourth important difference what you need to really look at, because this particular area, whenever you focus on the classical computing, you struggle with the large data sets because of the resource limitations under which you try to operate. Unless your resources are increased, your ability to process the things will be very, very less. But in the context of the quantum, you use a very, very focused way of handling the high dimensional data, and you try to improve the data spaces efficiently so that your quantum parallelism can be achieved. Last but not the least is the hardware. In the context of the classical machines, your silicon-based transistors are used, but in the quantum hardware, you use materials like superconducting circuits, photonic devices, and trapped ions. These are all plays a very important way under which you are trying to look from the comparison of the computing. This is a basic understanding one need to be aware when you really try to look at the changes under which you are trying to operate. Now, knowing about the differences is important that what is importance of the quantum solving the complex problems. We know that it has got higher capability. We know that it has got a higher, faster speed processing power. But can I pick up every problem on the earth? No. So, so it's important that you understand the critical problems what it is trying to solve and what are the capabilities of the classical systems. By leveraging quantum mechanics, you can solve this to a very predictable way. So particularly when you're looking into the optimization problems, wherever you say there is a performance issues and it need to be performed very, very fast to make the right decisions in a quick manner, you look at the option of quantum as an advantage, because classical has limitations optimizing the large systems, especially in the context of supply chain systems, logistic operations. These are all the NP hard problems in the mathematical world. While in the quantum advantage, algorithms are really focusing on the quantum approximation and optimization approach and quantum annealing approach, which provides faster approximate solution. They will be approximately arriving at that particular solution very, very quickly. The second importance is about the cryptography. You understand the limitation of classic approach. You have in the cryptography RSA, ECC encryption rely very heavily on the factorizations for the discrete algorithms. But the quantum offers you the advantage of using the Shor's algorithm, which can break their cryptographic systems. So any of the cryptographic systems today can be easily broken with a quantum advantage, the algorithms which are supported on the quantum, leading more pushing the boundaries of the development team, leading more towards the development of quantum resistant cryptography. That is the need of the hour. In fact, today government of India and many other governments are also focusing on building the quantum proof systems for the future, because once the quantum chips are made available, there is a huge possibility that ethical hacking team which is sitting on the systems, huge data, stolen data, they will be really able to unlock the 10 country data fast and try to reach to us. So that's the reason preparing ourselves for the future is very, very important. We have seen in the past about Y2K problem. The future is all about Y2Q problem you need to tackle, year to quantum. I don't know whether it happens in 2030 or 2035, but when it happens, you need to be ready with it. So hence, quantum shield and quantum technologies, utilizing and shielding your entire equipment, your network is very, very critical along with applications. The third important area where you see quantum solving classical problems or complex problems is drug discovery. Because the doctors who are involved need to do with a lot of proper parameter combinations, simulating the molecular interactions at different levels, and it is very computation intensive. So with the quantum advantage, you have algorithms like VQE. We are going to touch upon that, and quantum chemistry simulations can enable accurate modeling of the molecule. So that is the key. What you need to really take advantage of it. If you take a artificial intelligence, that is another important story one need to be aware. Processing any of the AI models today, you take machine learning models or deep learning models, training these AI models with large data sets take a lot of time. You need to do multiple iterations to achieve that objective. Instead of after doing that also, the accuracy will always be challenged. But with the quantum machine learning techniques, like quantum enhanced kernels it can really speed up the things and improve the efficiency. The entire time is crunched in such a way that you will be able to roll it out to the marketplace very faster. So big data analysis is another important domain where you see this quantum playing a very important role. Means in the classical, you have a limitation of high dimensional data sets as a resource intensive, which is valid. But in the quantum algorithm, when it is utilized in solving the linear systems exponentially faster. So HSL can be playing a very important role in doing that particular function. So in a nutshell, what I want to communicate is that quantum computing is a transformative technology which leverages quantum mechanics principles like superposition, entanglement, and quantum gates to outperform some of the classical computing in the specific domains. Their ability to solve the optimization problems really enhances the AI and accelerate the drug discovery, underscores its potential to tackle some of the industry complex challenges beyond the capabilities of any classical systems what you try to take. As the hardwares are getting matured and the algorithms are getting advanced, quantum computing will be playing a very pivotal role in reshaping these industries and the scientific research beyond the scenes. It's very important that you understand that. So if you know that, when you're trying to teach to the students, it's very important to establish that relation. Hence, I'm going to briefly touch upon one of the important thing about the classical machine learning. We're all familiar. I'm not going to get into the depth of this particular subject, but really wanted to make it much more meaningful connection I want to establish so that you really appreciate what we are trying to communicate. So if you try to take the machine learning, which is a subset of the AI today, focuses on building models that can learn patterns from data, make predictions, and also do the decisions without being explicitly programmed. Means you're not really programming, you do this. It's not a rule-based engine. It's learning and it's trying to make the responses and make the judgments based on the data available. Some of the key concepts in this area, what you see is about supervised learning. So you normally see in the supervised learning, the data sets are generally labeled, where the output is known, predictable. And the way it works is the model is trained on input-output pairs so that it can predict the output from the new inputs. So some of the key models you would utilize as part of this particular supervised learning is a regression for predicting the continuous values. Like you can predict the house prices, stock prices. Classification, predicting the categories, which is like a spam and non-spam emails. And today you see the supervised algorithms are heavily used in fraud detection, credit card fraud detection, image recognition, and sentiment analysis from your tweets or the Facebook chats. The second important concept which you need to be aware is unsupervised learning. So learning from unlabeled data where the goal is to identify patterns or the groupings. The model finds hidden structures in the data without any predefined outputs. Some of the key algorithms what you need to be aware, you might be already, the clustering and the dimensionality reduction. The groupings, the similar data points like customer segmentation, customer ethnicity, and the region, they all form as a clusters. And the dimensional reduction aims to focus on reducing the number of features in the data. Like one of the famous algorithms is related to the principal component analysis. We are going to touch upon that as well. So specifically in the unsupervised algorithms, you see the market segmentation, anomaly detection plays a very important scenarios under which we try to operate. The third important concept one need to be aware is the neural networks. This is very much close to the Gen AI angle also. So models which are inspired by the human brain. Basically, you're trying to model like how human brain could predict, and prescribe that, so that it is a kind of a connection of interconnected layers modeled with a specific set of neurons. So input data passes through these layers with weights so that they are adjusted to minimize the errors in the prediction. This is one of the important subject area because machine learning, deep learning, Gen AI, they're all interconnected. And Gen AI is a very, very subset of the deep learning. And within the context of machine learning, it's even more lesser. So you see this kind of networks are there in the form of feed-forward networks, convolutional neural networks, and recurrent neural networks, which are specified for specific things. Feed-forward is generally used where the data flows in one direction, does not come back. Convolutional neural networks specialized for image data, and recurrent neural networks where you are specialized for sequential data like time series data, text data. They all play a very important role in aiding in image recognition, and image annotation also, NLP and the voice assistants. So the fourth important area what you see is a decision trees. I believe some of you might be making a lot of decisions in your career, but decision trees, when it is programmed with a model, it will give us a very, very accurate answer based on the kind of it is trained. So today it is like a tree model which is used to make decisions based on certain series of conditions. So data is very much split up recursively based on feature values or maximize information gain. And you see some of the specific areas where we see the decision trees are leveraged is customer decision analysis and loan approvals are very, very much there. Likewise, I just wanted to briefly expose you to the reinforcement learning and enlighten your basic understanding about the machine learning concepts. So reinforcement learning is all about learning by interacting with an environment and receiving the feedback so that you keep on improving your model ability to respond much better. Support vector machines which are used for the classification integration so that you find the best boundary between the data points, and ensemble methods. These are generally used as part of bagging, which are the example is a random forest. You might use RF algorithms a lot for prediction for the multiple trees, and boosting. This is XGBoost focuses on correcting errors of weak models. So these are some of the primary aspects what you need to be aware as part of the classical machine learning concepts so that you will be able to really appreciate the way you are getting engaged. Now, I mean, knowing these things, what is the importance today in the machine learning? So in the various industries, are they really applying? Do you see these particular things as highly relevant or not? So when you start witnessing and asking that question for yourself, you will be discovering that yes, they are using it. So machine learning is truly transforming industries because it has an ability to provide a framework with a better decision making, improving their efficiency, and unlocking some of the new possibilities which were not there earlier. As I say so, if you typically take the healthcare applications, you can predict the diseases by looking at the radiology reports, and you can also personalize the medicines based on the treatment for that particular individuals, which is having the patient data context. You can tailor the treatment plan, drug discovery, and you can accelerate the overall research focus so that you will be able to predict the models much faster. So that what happens is you will be able to provide the outcomes which is desirable for the business. Now, finance is also another use case area which you need to be aware, because unless you know where we are applying, you will not be able to appreciate what algorithms to be used for what kind of a problems. Finance is where you try to see it in the fraud detection area, algorithmic trading area, and credit scoring area, because it helps in enhancing the security. It helps in improving their profitability for this by through the smart decisions. So they are not really focused on building something which is not used. The third category, what you see is about the application categories are autonomous vehicles. So autonomous vehicles, you talk about Tesla, which comes to your mind definitely, but there are other engines or the other models are also getting developed in the autonomous space. Semi-autonomous space now, but there's not a strong belief to make it more autonomous because the regulatory authorities believe if there is an accident happens, it is very, very difficult to penalize anyone because no one is really driving. It's a machine which is driving. So, and autonomous vehicles focuses on the object detection area so that it can identify the pedestrians, vehicles, obstacles Now, one of the prime example I think is about the CCTV footages which does this, but how you are able to detect that and make the decisions is something you need to really look at. Route optimization is another thing. Decision making, where you are able to look into the safe navigation in the dynamic environments. So these things really, when it is really programmed in that context, now you start seeing that it will bring down and improve bring down some of the anomalies and improve your KPIs with respect to the reduction in accidents or reduction in transparency and efficiency as part of autonomous vehicles. The fourth important thing is retail and e-commerce. Very, very heavily uses machine learning to your core. You take Amazon, Flipkart, Chroma, or shops, any particular today web applications you take or the mobile applications you take, they are using classical machine learning because it really enhances the customer satisfaction. You will be able to manage the inventory well, manage and provide the required recommendations, and also forecast the system for the future so that you'll be able to optimize the price, keeping the fast moving and slow moving goods. These are the decisions which are required for the organizations to be staying in a profitable manner and not getting to the trap of recommendations which are coming only by face of value but not by the face of fact. The fifth important application area where you need to be aware that machine learning, classical machine learning in the various industry which is uses, we are going to touch upon is a manufacturing area. Some predictive maintenance, quality control, and supply chain optimization are the three important categories where machine learnings are applied so that it can reduce the downtime of the unit and also improve the product quality of the unit. These are very, very critical for the success. So today, honestly speaking, machine learning has become a very, very indispensable tool across the various industries because it is driving the innovation and efficiency from healthcare to the autonomous vehicles because it is having the ability to learn from the data and improve over the time to make the right decisions you leveraging modern technology. As data availability grows and machine learning techniques evolve, its impact not only deepen, but it also solves some of the increasing complex problems in the entire nature. So this is something which you need to be really aware of the fact because once you know this, you have an opportunity to understand why integration of the quantum computing with classical computing is really making sense. Because we will come to the quantum machine learning, but it is important that you understand the computing level, which is really bringing the speed, solving complex optimization problems. So when you really look at the quantum computing and machine learning, if you're trying to look at the isolation, you see it as a different entities, but they are the two transformative forces and technologies integrating creates a quantum machine learning, which truly leverages the quantum mechanics to address the limitation of the classical ML algorithms. Particularly for the large scale organizations, you see integration plays a very important role because one, you see the computational speed. We told in the beginning also, right? The speed is the key because it has an ability to look at the classical ML models and require significant time and attention so that it can be trained, inference, and can be built so that you are able to deal with high dimensional data in large data sets. While the quantum also offers an advantage because you heard about the technique called superposition, right? Superposition and quantum parallelism will help in unfolding some of the multiple possibilities. And algorithms like Grover's algorithm can really speed up the searching of a unsorted database time. And it can really compare it with the order of n for classical algorithms. It can come down to the order of square root of n also. So that's how you start seeing this particular area of thought, which can play a very, very important role in solving some of the complex optimization problems. Having said that, it's important that you know what does this solving complex optimization problem means. See, today, optimization tasks are computationally very intensive from classical systems, especially in the high dimensional spaces. You may want to find out the shortest path. You may want to find out the minimizing the errors in the machine learning models. Very, very hard to predict and very, very hard to get to the core of it. So solving complex optimization problem requires to leverage some of the algorithms like quantum approximate and optimization algorithm and quantum annealing, which are exploring some of the vast solution space, which are bringing a lot of efficiency and change in the entire classical counterparts. So you see some of the supply chain with thousands of interconnected variables are feasible within the quantum methods. So these are some of the critical elements as far as the complex optimization problems are considered. But if you try to look deep, you see another important thing is the large scale data processing. So classical machine learning models, when you look at it, due to the memory condition or due to the computational constraints, you have a difficulty to process them. But quantum is not like that. It uses something called qubits, which is really allowing the exponential scaling in the data representation and enable efficient cost optimization or computation in the high dimensional spaces as well. So we strongly use a principal component analysis tool to reduce the dimensionality of data sets while preserving some of the critical information to a great level. Last but not the least is the improved pattern recognition and the generalization what you need to really look, because the algorithms like quantum enhanced kernels in the support vector machines context, it allows the machine learning models to identify and define the patterns in datasets that are very, very hard to separate and separate the classicality aspect. So the quantum kernels are very, very heavily used as part of the satisfying the accuracy of the information of the models or accuracy of the complexity of the data sets, so that in the context of healthcare, you will be able to determine the genomic sequence at a very, very faster pace with high resolution images. So these are some of the important elements which is really promoting us to look at the quantum machine learning or quantum computing to integrate with the machine learning. Having said that, now it's important that we delve quickly into the classical systems in the machine learning context, because these are key for the success of your next level of understanding. So before I go there, I also wanted to touch upon some of the important concept called when you're integrating, you also need to really look at better handling of the probabilistic models, which is important, because whether you're choosing what kind of a probabilistic models like Bayesian models or other things, you need to evaluate that and utilize as part of your overall recommendation engine. Without that knowledge, utilizing will really not fetch you the kind of a speed, or it will not able to fetch you the kind of a need what it can really address. So any questions so far?
Actually, participants are on mute, sir.
Okay, no
They
problem.
can ask the questions
Put down
in the chat.
you can put the questions on the chat window. I will be able to pick it up as I progressively move, or at the end we can do that.
Okay.
So, okay. So coming to this context, just wanted to iterate the thought that machine learning is broadly categorized into supervised, unsupervised, and reinforcement learning, and each of them has got a different tasks, and the data structures are completely different. So when you're looking into the supervising, as I said, it is a model with the labeled data sets, and both the input data and the desired outputs are also labeled and known. So some of the classical techniques which are leveraged is the regression model and the classification model, because regression can help in predicting the continuous values. You need to know the purpose behind the model, how it works, what are the different use cases where it can really fit. Don't force fit the model where one use case to another. Important that you know the purpose so that you can apply it. So the purpose of the regression is predicting continuous values. The model can learn based on the relationships between the input features and the output. So by it can reduce the error to a large extent. So you can predict the house prices based on the size and location. You can forecast the stock market trends. You can also use some of the methods like a linear regression method or polynomial regression method in this context. And in the classification area, you utilize this for the categorizing the data into predefined classes, because the model is responsible for assigning the labels to the input based on the patterns during the learned during the training, or during the reasoning also. So some of the key example is email classification, disease diagnosis, so that you will be able to classify those data sets and make the call accordingly. Some of the prominent algorithms which are used by all the people is support vector machines and the decision trees. Support vector machines, something like it can help you in finding the hyperplane that maximally separating classes in feature spaces. And it works well within the context of linear and a non-linear separable data space. Decision trees, it's like a tree structure, what you've seen, I heard about. It's split based on the feature threshold so that it is easy to interpret and prone to the overfitting area. The second important thing I'm reiterating is unsupervised learning, because in this area, the techniques what we leverage is clustering and anomaly detection methods, which are very, very popular. and or the dimensionality reduction also. So unsupervised learning is used when the data lacks labels. You don't have a labeled data, unstructured data is existing. The goal is to uncover hidden structural patterns and also look into the grouping of the same into the data. So if you look into the first technique, clustering, it groups similar data points together so that it can really work faster and quicker. And market segmentation, image segmentation could be some of the examples in this area. And the algorithms which are leveraged is the k-means algorithm for achieving the clustering concept, k-means clustering algorithm, so that it can divide the data into the k clusters by iteratively updating this cluster method so that it can arrive at the goal faster. The dimensionality reduction is another important technique used in the unsupervised learning because the purpose is reduce the number of features while retaining meaningful information. So whenever the MVP or minimal functional product is getting developed, dimensional reduction can play a very important role, especially in the context of high dimensional data in the 2D and 3D images when you're trying to deal with, or it is trying to reduce the computational intensity or complexity in the ML models. You use dimensionality reduction method as a common way of achieving it. Common algorithms in this space is a principal component analysis. You might be seeing this principal component analysis in the quantum learning also. So these are some of the important things in the reinforcement learning bucket. The third bucket is a reinforcement learning, which involves learning by interacting with the environment to achieve a goal. It is a model on a feedback loop where an agent takes actions to maximize cumulative remarks. As you know, as of yesterday, Gukesh was one of our world champion in the chess, the youngest world champion. Chess is one particular area where the models can learn by themselves by practicing it multiple times. So likewise, the Go game was also using the reinforcement learning method, where it was ultimately able to beat the champion of Go. Go is a very popular game in China. So in the context of reinforcement learning, you normally see the Q learning method, which is learn the optimal actions to take in different states to maximize the rewards. So the agent learns from the Q value of each state so that it can represent the expected outcome rewards. You see, this particular thing is heavily used as part of training the robots to walk, optimizing some of the logistic routes. Likewise. So you see the comparison I've given out for your reference where you can see the input, data, goal, and the common applications. Those will be the talking points for you when you're trying to teach to your students or absorb your own learning methods. Because each ML technique serves for a specific purpose, you need to understand these techniques and allow that machine learning practitioners to choose the right approach based on the problem or data availability or the desired outcome. Then these things will be much more powerful than what you try to really look at. Now, knowing this, it's important that we also touch upon some of the limitations. Limitations, very often we try to ignore the limitations, but it's important that you understand the limitations of this machine learning so that will really unfold your thought for the quantum machine learning. Why we are going and learning quantum machine learning, you know once you know that limitations. So it's based on the overall capabilities of the machine learning, it still faces certain challenges. It has certain areas where its effectiveness and scalability is always challenged. Some of the key limitations which are observed in the industry is the computational resources, difficulties in handling the large data sets, training and optimizing the inefficiencies, and problems with the overfitting and generalizations. This is the common problems what we normally see. So if you typically understand the challenge, machine learning algorithms, especially the deep learning, request significant computational power. No one will deny it. You need GPU power for your ML and DL algorithms to run. With a limited data set, it can run on CPUs, but GPU can accelerate things. So there is a huge amount of hardware dependency, and CPU all comes into the action. There is a huge constraint on the memory because the kind of a number of parameters under which need to be trained, bandwidth becomes a challenge. It can be choked. Energy consumption is another area where you can see the large modules for energy are intensive. You can raise concerns about the sustainability. So the BERT transformers are leveraged as part of computational capabilities and help the small organizations to embrace it. So the second important thing in the limitation is handling the large data sets, because any machine learning, we know that handling large data sets is a challenge. The training time is a challenge. The optimization is also a challenge. So as the data is growing, as the population grows, data grows, humongous data comes day in, day out. In the healthcare area, finance area, e-commerce area, how do you try to pace with that change? How do you be able to outpace that entire thing with your compute capability so that you are really hungry for the data to process next? That's where comes the quantum, because today with the classical systems you have a data pre-processing limitations. Training the large data sets is computationally expensive, and that can be countered through the quantum learning. And training time is another thing. Longer training times is required because multiple iterations are encouraged to get the accuracy of the system. And optimization issues you need to really look at and solve it, because it may say that optimization techniques like grandfather and this a descent which may be struggling. Now there is a lot of optimization problems. Whenever there's a huge data set involving the optimization problem, you can consider quantum as a source of thought process to solve the problem. So, and the third important category is the overfitting and the generalization problems. So when a model learns training data well, including the noise and outliers, leading to poor performance of any kind of unseen data. That's where you see some of these models playing a very important role, because the accuracy and the quality of the data play a very important role in ensuring the right results are given out. So today you see a lot of neural networks which are developed are trained on the small data sets of images. Start trying to memorize the things specifically so that it teaches rather than the learning general patterns. So that is what the deep learning. But if it is a generative AI, it's something completely different. So some of these generalization problems are also a limitation in the classical systems or computational systems today, but that can be countered to a great level when you are trying to migrate to the quantum level methods. So in generalization, if the model has not seen a specific set of data, it cannot generalize. The unseen or new data is always a challenge under which you need to really operate, because the feature selection can be poor. The lack of diversity in the training data can be a challenge. The overfitting the described noise is also a challenge. These are certain things which could really play a very important role. And in order for you to address these challenges, looking for computational resource capabilities like frameworks like TensorFlow, PyTorch can play you. And handling the efficient handling on the data sets can play a very important role, because you can look at the option of batch processing, mini batching, gradient descent, or and employing some of the data governance policies and data augmentation techniques can also improve. And you can mitigate the overfitting challenges by applying the regularization techniques and cross-validation techniques. And you can also improve the generalizations by ensuring the data sets are representing the real world, simplifying the model architectures, and fine-tuning and pre-training for the models for the domain-specific uses. So the bottom line, what I want to convey is some of these limitations need to be addressed, and you need to balance computational resources, algorithms, which can really improve your robust data practices to a great level. Then only you'll be able to advance to the TPUs, tensor processing units, and graphic processing units, along with your smarter algorithms, which can really mitigate these challenges to a great level. So, having said that, it's important that I also touch upon some of the second part of the talk which I want to do. This it's on the introduction to the quantum machine learning. Now, what is quantum machine learning? Why it is important? Why need to be? What is the role of it? That is what we are going to look into this particular section. So, quantum machine learning is an interdisciplinary field which combines quantum computing principles with machine learning techniques. So the general objective of this particular quantum mechanics is to enhance the efficiency and capability of the traditional machine learning tasks. So the key thing is what you need to really understand is the quantum states and superposition. So when you look into the quantum states and superposition, you start embracing the fact that the superposition allows quantum bits to exist in multiple states simultaneously. Like unlike 0 and 1, it also has 0, 1, 1, 1, or 0, 0 likewise. And in the optimization problems common in machine learning, where you try to see these quantum algorithms can assess many potential solutions concurrently. Even if you're trying to go into the maze, right? A maze, when you're trying to start from here and reach here, whenever it encounters two different paths, it gets duplicated or cloned so that it can work in parallel and achieve that objective. Another solid example I can give you is about if there's a huge set of library in your college also. If a librarian is asked to read a book, he will read it sequentially. But in quantum, it can read all the things in parallel at one go. All pages it can memorize at one go. The quantum entanglement is another thing. Just getting into the depth of the understanding, we slowly get into the more depth as we progressively move. So you see that quantum entanglement allows qubits to be interconnected. So that state of one qubit can influence another one. So the interconnectedness can improve the data encoding and representation of the QML. The third important area is a quantum parallelism. When you look at this quantum systems data can parallelized. I mean, you can in parallel due to their inherent properties. So quantum core model can potentially train on multiple hypotheses simultaneously so that it can speed up its training tasks. But when you, the fourth important area where the quantum mechanics plays an important role is amplitude and amplification. Quantum mechanics can amplify the probability of some of the key solutions in search space, which can be utilized for faster decision making in classification or in the clustering tasks. So that is some of the basic things, but you need to understand why quantum machine learning plays a very important role. What it offers to me, which other systems are not really offering. Speed. Speed, because quantum speed is the ability of the quantum algorithm to solve certain problems faster than the classic counterparts. That is evident. Now, some of the popular algorithms which are there in the quantum world is Grover's algorithm. You might be hearing with some of the faculty already. If not, you might be looking at it. So it can search an unsorted database in an order of square root of n time compared to the order of n classically. So accelerating the search task in machine learning with the hyperparameter tuning can be a great story on the Grover side. Shor's algorithm on the other side is efficient problems like prime factorization. Democratizing the quantum advantage in optimization task is a critical thing, and that plays very important role. And some of the quantum advantages which is really helping you in this journey is the exponential efficiency, the speed under which it is trying to operate, the speed under which it is trying to look into the high dimensional data sets and represent that particular quantum states in parallel and achieve that object. Similarly, in the quantum enhanced kernel methods, you outperform the classical kernels. So in identifying the patterns in the data sets, that is a key, and support vector machines utilizes this to create classification model. The third category is about the quantum data processing. Quantum computers today can handle data encoded in the quantum states. This allows a lot of faster manipulation, faster transformation of the larger data sets. That's where you see principal component analysis are used for the dimensionality reduction. Fourier transformation is used for signal processing tasks, so that you appreciate the quantum machine learning really circuits compute these transformations to an efficient manner. Some of the key applications you see in the quantum machine learning is utilizing the ability to train the things in a faster way for a massive scale of simulations you can consider, and you are able to utilize and improve the accuracy of these models because it can uncover the hidden patterns and correlations in data and enhancing the prediction accuracy. And some of the new paradigms in machine learning can also be leveraged so that quantum annealing techniques, which will really pave the way for new algorithms and methods. And finally, the applications like financial modeling, drug discovery, recommendation systems, and climate simulations, all these things have a very good promise and an outcome because of the leveraging the quantum machine learning, because it revolutionizes and it also provides a lot of applies a lot of quantum mechanic principles. While this is currently, I would say, very nascent in stage, but future is very positive in this area because it's one of the next transformative technology which is going to rule the world after Gen AI, what we are witnessing today. So next few slides, now we are going to touch upon some of the important quantum machine learning algorithms. We'll go one by one so that you will be able to appreciate this and use this in the solving some of the problems. So quantum machine learning employs quantum computing principles to develop efficient algorithms for classification, clustering, data encoding, and neural networks. So one of the key example I would like to give you is about quantum classification. I'll go each one step by step. So some code-based constructs are also available for your knowledge. But in a brief, I would say that quantum support vector machines are the examples of the quantum classification techniques. Similarly, quantum enhanced learning, we are going to witness about QK means. For data encoding, we are going to touch upon principal component analysis. For neural networks, we are going to touch upon the quantum constitutional convolutional neural networks, that is a QCNN, what we prominently call. So let's see each one so that you will be able to appreciate what does it offer. So in each stage now I'm going to touch upon the definition part, probably the flow, and some of the use cases which is relevant in the context. So if you typically take the quantum support vector machine, the purpose behind it is used is to classify data into the categories. So using quantum kernels to enhance the traceability or separability of the complex data sets. The way it works today is about, if you see this flow also now, data is encoded into quantum states using the feature mapping circuit. Then a quantum kernel function calculates inner products of data points in a high dimensional quantum feature space. Then the classification boundary is determined using the classical optimization techniques. So when you put in this kind of a flow, you will start be able to relate it and try to see how it is really helping you. And one of the function where you can use support vector machine is in the financial firm, especially for predicting the stock market trends. And today, when we're seeing a lot of AI-driven recommendations are coming in the stock market, predicting the maps, predicting the market indicators, and trying to analyze it on your behalf. The second important algorithm I'm going to touch is about the quantum enhanced clustering QK means. So this is very interesting because the way what you're trying to see is you see this particular application. So a retailer, let us say taken a retailer who applies QK means for segment customers based on some of the purchasing behavior using quantum distance measure for faster results. Basically, you try to measure how much quantity purchase, what is the price every time he visits, what is an average 10,000 rupees, 20,000 rupees, 30,000 rupees. Based on the nature of his transaction, you know whether it is a premium customer, repeat customer, or a customer coming for the first time. All these things can be really, really quickly analyzed through the QK means to the great level. So summing it up for that QK means context, basically you use QK means when there is a need for you to partition the data set into K clusters, and you leverage the same by using the quantum speedup. The way you try to look from the overall implementation standpoint is data is represented as a quantum state, and then quantum distance or similarity measures are calculated between the points. Once you do that, then you try to take the quantum algorithm, assign points to the clusters based on the nearest quantum centroids. And these centroids then are updated iteratively using the quantum computation techniques until it tries to converge. So this process is done so speed that market segmentation, image segmentation can be done using the quantum learning to a great level. That are the problems what you need to really solve. Having said that, let's look at the next one is about the quantum data encoding. And here is where the principal component analysis is used. Very interesting algorithm, one of many of the people's favorite also, I believe, because it reduces the dimensionality of the data sets while preserving most of the significant features. Now, normally when you try to model any particular image or a segment, there might be a lot of features, but not necessarily all features you are going to test it. Not features, all features will be coming as part of the query. So that reduction is where the PCA can really help, because it works using the data covariance matrix by representing it in a quantum operator. And eigenvalues can be leveraged, or eigenvectors can be extracted using the quantum phase estimation. And these principal components are really identified so that you can see the downside of the higher eigenvalues. Some of the key examples I see is about the gene expression analysis, reducing the features for training ML models. They are all playing a very important role, and bioinformatics researcher utilizes this QPCA, principal component analysis, to analyze and generate the data and focus on some of the critical gene expressions. Very, very popular in nature. The fourth important thing which you need to be aware in the quantum neural networks is quantum convolutional neural networks. Why it is important, how it is done, what is the purpose of it. So keeping the purpose in mind, it helps in implementing the neural networks using quantum circuits for tasks like image recognition. So these are the popular things which are used as part of the communication media sector, and not also used as part of the CCTV feeds analysis also. So you can solve that problem using the quantum. So how it really works? It works in data encoding the quantum states, then convolutional areas extract local features using some of the parameterized quantum gates, and it will try to pool the layers, reduce some of the quantum feature maximum, and then fully connect the quantum layers output prediction. So all these things are the sequential steps it looks like, but it can do it in parallel, and you apply this particular thing as part of the image classification and pattern recognition area, and be one of the best algorithms which can help the manufacturing as an aid. Manufacturing industries are expected to use QC/NN because it can identify the defects in the manufacturing plants and the operations. It can quickly leverage some of the quantum convolutions for superior pattern detection techniques. So these are some of the key things which will really help in ensuring that a QSVM, that support vector machine, K-means, PCA, CNN, are really paving very, very faster. NIST is releasing the new versions of this particular algorithms to stay relevant in this context. Otherwise, the quantum algorithm is going to rule the world and we may be falling back. So there is an immense potential in these particular fields because there is a high dimensional data processing is possible, pattern recognition is possible, optimization is possible, which can really help in face the limitations boldly, to utilize the research advancements and take it to the next level. So these are a few things very important from the quantum machine learning angle one need to be aware of. Having said that, let's go a little more deeper. Little more deeper where we also see the constructs. I believe we are able to see the code base. See, quantum approximation and optimization algorithm. This is one of the famous algorithms which is today. But before you go there, let's understand what is this optimization is all about. Optimization problems which aimed basically to find a solution from a set of possible solutions and highly prevalent in fields such as take logistics, take some finance and machine learning. They all play a very important role. So quantum computing here is very, very promising because it approaches to solve these problems more efficiently than ever. And some of the methods I have explained here for your own benefit. So when you get an opportunity, I want you to utilize this code constructs to apply Qiskit or Penny Lane or any of the algorithms which can or the frameworks which can allow you to program using the quantum. Qiskit is very, very popular in our world, so it's easy for you to get access to it. So in the QAOA, which is a quantum approximation and optimization algorithms, it's a kind of a hybrid quantum classical algorithms, particularly used to solve some of the combinational optimization problems. It operates by encoding the optimization problem to quantum systems, Hamiltonian, and finding an approximate solution by minimizing the overall cost function. The cost is a very, very important factor what you need to look when you're looking at the approximation area. So there are multiple steps which are there involved. Problem encoding. When you look into the problem encoding, it represents the optimization problem as a cost Hamiltonian. Initial state preparation is another one because it helps in initiating the quantum system in a superposition state. Evolution, because it helps in alternating between the applying and maximizing and mixing the Hamiltonian state for a fixed number of steps. Fourth, but not the least, is the measuring the quantum state to extract the right solution. Some of the famous problems which are used using this particular technique is max cut problem. You just Google around it, where it gives you the goal that it has a partition a graph nodes into two data sets, so that number of edges between the sets is maximized. So it is not about cutting the node into two parts. It's about maximizing the data sets in a the intent is to maximize that. So on the right hand side, I gave you some sample Qiskit code which can work when you try to put it up in a very, very layman terms. The second important algorithm which I want to touch is about a variational quantum eigensolver. We witnessed this in the beginning of the talk. Now we are going to touch upon. So VQE very, very important hybrid algorithms, which will find the ground state of a quantum Hamiltonian method, often found in the chemistry or in the optimization area. Some of these variation principles are very, very critical because they say it will ensure that the energy is computed in a very upbound manner at the truth of ground state energy, what you try to look at. The critical steps which are involved here, one need to be aware is preparation, measurement, and classical optimization. Because in the context of preparation, you're choosing a parameterized circuit, quantum circuit. It's not a normal circuit, quantum circuit to represent the trial wave function. And then you try to use the Hamiltonian function to get the expectation value. Then you adjust the circuit performances to minimize the overall energy. That's a process and a protocol what you need to really follow, and especially this variable uh, quantum eigensolver is used as part of the portfolio optimization or supply chain optimization. Also it can be used. So the Python skills might be good enough for developing the VQE based algorithms. The third is about the quantum annealing, very, very popular method in the quantum world, which I wanted to really help you understand that. And when you look into the quantum annealing, it finds the ground state of a problem. And using the Hamiltonian, it's by slowly learn by the quantum system parameters. So unlike some of the gate methods which we have seen, there are two gate methods we have seen, right? Quantum algorithms, quantum annealing is a hardware specific approach. It's not a software specific. It's implemented in the systems like D-Wave for the better performance. So, but other systems you need to manually go and implement it. So D-Wave is an Australia-based company. It provides the 2 qubit machines to 128 qubit or 256 qubit machines also. So today, when you look into the walk back and look into the steps, problem encoding, annealing, and measurement are some of the important steps in this entire journey, which can help you to transition from the initial Hamiltonian function to the problem Hamiltonian method also to a great level. And remember, this particular optimization challenges can be leveraged as part of some of the key goals or job scheduling areas, which can bring in a lot of transformation in finding the optimal configuration. So there's again a code base which is being given. I just wanted to bring your attention that when you're looking into such kind of things, you also need to compare. The compare means basically when to apply QA/OA, when to apply variable quantum and eigensolvers, when to apply quantum annealing. Very, very important. If you don't know the application part of it, it becomes a challenge. So you see that the top two ones are the gate based, last one is annealing based. Two ones are provided to the universal QC, second one is quantum wave, but it really solves the problem today. The problem what it solves in the QA is a max cut problem. And in the VQE, for the especially in the healthcare, in the molecular simulation, you can utilize, and especially in the manufacturing area, you can use quantum annealing for job scheduling and traveling salesman problem. These are some things which can really big things. Coming to the third section and very critical section for because this is where our core theme is lying, where you are trying to integrate the quantum machine learning with the classical systems. So when you look into the classical systems, it's important that you start appreciating the fact that how this quantum machine learning can be really leveraged. So if you see, there's a huge amount of responsibility divisions which are there here today. So this responsibility divisions plays a very important role. The division of responsibilities help you to understand where to apply, when to apply, and whatever you witnessed as part of that, it's important that you merge the concept of the classical systems and the machine learning concepts. It will really help you to look into the focused way of understanding and appreciating these things. So, so you see this in the hybrid quantum classical machines. The classical concepts is all about trying to touch upon the hybrid way of looking at this. The division of responsibilities advocates the fact that how the quantum computers or classic computers are leveraged to be understood. These are some of the things. Now you normally utilize these particular things, but you don't know when to apply, what to apply, and where do we really apply. So having learned these things, let me walk you through some of these examples, storylines, which will give you a very good amount of understanding about the integration of the hybrid quantum classical systems, which can really play a very important role in this entire journey. Okay. So, I mean, 1 minute. So in the hybrid quantum classical approaches, it tries to combine the strengths of the quantum and classical computing. So this approach is very, very behavioral centric because uh, the quantum computers has got something called concept called NISQ concept, noisy intermediate scale quantum, which are limited in number of qubits or the error rates. By offloading some of the specific tasks into the quantum systems, you can rely on the classical systems for other hybrid model functionings. So there are certain things can be done with the classical things. There are certain things can be done with the quantum, and you can merge those things. That's where the divide and conquer method or division of responsibilities comes in. So you try to divide some tasks which are suitable for the quantum mechanics like optimization, sampling and solving linear systems so that you can get that speed and advantage of using their algorithms. While you can look into the classical computers to perform tasks like data pre-processing, model training, and large-scale storage, so that you can still take the advantage where quantum is not really playing an important role, which is not significant. So in the hybrid world, what happens is generally you try to pre-process this data using the classical computers, then use the quantum processing units to handle specific subtasks so that you can evaluate using the quantum states and solve some of the sub problems or critical problems. Then the results are fed from the QPU, the quantum processing units, and fed back into classical systems so that you can use a further computation refinement and decision making, which is much, much easier. So especially if you take the optimization problems, right? You can use quantum systems for using the quantum approximation optimization QAOA algorithm to find a global minimum in a combinatorial optimization problem. While you employ classic solvers, which can play a very important role to scale them for the larger data sets also. So having said that, let's look at some of the classical integration frameworks because when I want to apply this, I need to know where to apply and what are the frameworks available today which I can really use. So we'll touch upon some 3 to 4 classical integration frameworks. So one of the famous framework which is used is a TensorFlow Quantum. So this is typically developed by the Google in a very collaboration with Xanadu, where they extend the TensorFlow, enabling some of the development of the hybrid quantum classic machine learning models. The key features what it supports today is it supports the simulation of the quantum circuits, it supports the integration with the classical machine learning models, and it also facilitates automating differentiation of the quantum operations so that you can allow gradient-based optimization to a greater extent. I mentioned about the use cases here, which is about the quantum enhanced neural networks and also the quantum kernel methods for classic. And there's a sample which has been given. If you try to look into the Python code base which is given, it uses Circ as a framework. Remember, Circ is another framework, just like a Qiskit. You have a Circ as a framework coming from the Google, and you can use that to query the things and to create a quantum data set, and you can also provide the hybrid quantum classical model. That is the enablement it tries to offer. Very, very efficient way of bridging the gap and work in quantum world and the classical world together. That's a best combination what you can really look at. The second important framework what you need to be aware is Penny Lane. So this Penny Lane is very, very popular because again, this is developed with Xanadu, but they had a designed for differentiable quantum programming. So basically they wanted to allow quantum circuits to be integrated with machine learning libraries like PyTorch, TensorFlow, and IAX model, JAX models, and JAX frameworks, in fact. And the features they were more focusing on supporting the gradient descent using the backpropagation methods. And it was working with the hardware from various providers, not limited to one hardware like D-Wave. It was working with IBM Q, Rigetti, Xanadu had its own hardware, custom hardware, which was there. They were leveraging that. So Penny Lane specifically used in the context of hybrid quantum classical optimization and also for the variational quantum algorithms. These are typical use cases, what you can really look at. I gave some of the Python code construct using the Penny Lane for your own reference. You can use that to define the quantum node And once you define the quantum node, you can use it for the hybrid optimization approach by calling the gradient descent optimizer algorithms also. The third very, very popular framework, I believe some of you might have already got exposed, is a Qiskit. So I would encourage you to download Qiskit and experiment in your labs. This is an easy way of learning quantum because it has been developed. The IBM Qiskit has got a very, very comprehensive. Microsoft also released a quantum SDK and the quantum computing hardware. And it's primarily designed for the IBM hardware, but it provides the tools to define for the quantum circuit design, simulation, and execution on the IBM Cube, which is the quantum hardware, what they call. So the key features which are there as part of this Qiskit is it offers or includes the modules for the quantum machine learning, optimization, and chemistry. And it supports variational hybrid algorithms like VQE, that variational quantum eigensolvers, quantum approximation optimization approaches. And basically it is used whenever you see an opportunity for the quantum chemistry area, see an opportunity in the quantum enhanced optimization area. And code construct I used similar in the Qiskit. So it's not a big programming methods. What you need to be aware, the smallest set of cycles of programming also can help you to define the Hamiltonian function and then define the variational ansatz preparation. That preparation is required. And once you do that, then you try to define the variable VQE and try to use the eigensolvers to solve it. So this has got huge amount of benefits. When you try to look from the benefit standpoint, there are huge. These frameworks, when they are put into the right context, it plays a very, very important role. And one need to really appreciate the fact that quantum classical approaches can help you in a hybrid world to scale the systems, to build the efficiency, and it can really, really manage the hardware compatibility and offer a lot of flexibility. So hybrid quantum classical approaches represent a very practical way to harness some of this power of quantum computing without being constrained by current hardware limitations. So TensorFlow framework, or Penny Lane or Qiskit are some of the developer aids and researchers aids to integrate quantum computing into the classical workflows so that you can really drive the innovations in optimization function, drive the innovations in the machine learning and beyond. So you're not limiting to the hardware, but you can still do certain things with this approach. So focusing forward, I just wanted to touch upon some of the hybrid algorithms in the quantum machine learning area, because these are the certain things plays a very important role. So when you look into the hybrid algorithms for the image recognition space, you see quantum enhanced convolutional neural networks. So QCNNs are generally integrated with the quantum circuits into the layers of classical convolutional neural networks. They leverage some of the quantum states and operations to process the image data so that it is more efficient, more faster, and particularly it has an ability to extract the features and classify it. The way it works is it has got some stages like a data processing stage, then where the data processing stage, image data is pre-processed and encoded into quantum states. Then the next stage is quantum convolutional, and where the quantum circuits acts like a convolutional layers, which can extract the spatial features. The third is about the pooling layers, where the pooling can reduce the feature map size so that by selecting the most significant features are really utilized there. And then the fourth important thing is a fully connected layer. So where the classical or the quantum fully connected layer can generate the final outcomes and predictions. So they have a greater utility, and QCNNs can help in recognizing the handwritten digits. Just like you upload an image in the ChatGPT, you might be finding that it is able to interpret and immediately give you. That uses the CNN, but if you have a huge amount of data to be processed, that's where the QCNN can play a very important role. Some of the penny lane concept I have, code snippet has been dropped here. That can be completely leveraged. Penny lane, what we have seen in the past, right? That can be leveraged as a understanding this handwritten digits much more faster. The second important real world use cases in the hybrid system is the quantum enhanced data classification. So that's where you see that quantum support vector machines can be used because it can extend by using the quantum kernels and enable some of the better separability of the data into high dimensional feature spaces. So the way it works is it uses data encoding where data points are encoded into the quantum states. Then it uses the quantum kernel calculations, calculates the inner products of the quantum states in the, there's a space called Hilbert space. It's a subject, you can really explore that. The third stage is about the classification as part of the flow, where the classical SVM can use the quantum kernel matrix to define the decision boundary. You see the quantum, you see the classic. Both these approaches are used in this hybrid context to solve the problems, and especially in the fraud detection and the disease diagnosis, you can leverage this, classifying the cancerous and non-cancerous cells, where fraud detection can use the quantum area also. So this is the thing. The third important area is solving some of these optimization problems. Now we know that optimization problems can be typically solved by the quantum. One of the problem we all know in the education sector is the traveling salesman problem, right? Where you wanted to find the shortest route to visit all the cities and return to the starting point. So quantum approximation and optimization algorithm can be typically used to solve the TSP, that is a traveling salesman problem, by encoding the problem into the cost of Hamiltonian and finding the minimum energy state so that it understands the route under which it need to traverse. So the the portfolio optimization is the second problem in the optimization of what you can really look the stock market portfolio, the mutual fund portfolio, where you're selling the different assets to maximize the returns and you minimize the risk. Today, many of the financial advisors leverages these optimization approaches. I'm not saying that they use quantum, but when you are having a large scale of data sets at a corporate level and other things, this can play a very important role, where quantum annealing or quantum eigensolvers can identify the best portfolio allocations by solving the problems through the quadratic unconstrained binary optimization, QUBO formulation, what we call, that can be used, QUBO. So this particular things can be used to use the Qiskit. It offers you very good programming techniques. So bottom line, what I want to convey is, in the hybrid quantum classical algorithms in the real world, you can look at QCNN to enhance feature extraction and image processing tasks, QSVMs for improving the classification accuracy for complex data sets. Quantum optimization methods can tackle problems like traveling salesman problem and portfolio management problems more efficiently. So this kind of an approaches can give you and provide you practical benefits, and the outcomes are very, very fulfilling and compelling, which can be really benefited for all the people. As I say, it's important that you understand the benefits. The benefits are enormous. So when you look into the benefits, the quantum computing really offers transformative advantages over the classical systems today. And it could be the accelerated computation, enhanced feature extraction, and the ability to solve problems that are infeasible with the classical systems alone. Let's see, if you're looking into the accelerated computation alone, it can help in where as I mentioned here, it's about quantum computers can exploit superposition and parallelisms to perform computations, which is correct. But the way it works is, in the superposition space, qubits can represent multiple states simultaneously, allowing quantum computers to evaluate multiple solutions in parallel. That is a key advantage benefit. In entanglement, you can correlate qubits, share information instantly, so that you are enabling more efficient problem solving. In the speed up algorithms like Grover's for unstructured search or shows for the factorization can outperform classical counterparts exponentially and quadratically, because the speed is a key there. Especially if you're trying to look from the cryptography angle, Shor's algorithm can factorize large number exponentially faster. Search problems, when you're trying to look at Grover's algorithms, can speed up database searches like at a scale of order of square root of n when compared to order of n. So financial model, it can really use. Similarly, enhanced feature extraction. This is where you see quantum systems are really excelling in a great way. The way it works is the quantum states, high dimensional quantum states can allow rich data representation. Quantum kernels can enhance kernels for support vector machines so that it can transform data into a high dimensional feature space. Quantum principal component analysis, PCA, which can identify dominant areas in data efficiently by using some of the quantum operators to compute eigenvalues and eigenvectors. So these are few things from that. So basically you see that quantum enhanced feature extraction can be used in the medical imaging, NLP areas, so that it is highly beneficial because it helps in pattern recognition and image classification. And solving some of these problems which are feasible with a classical system, which are not feasible with a infeasible or not feasible with classical systems alone, also another area what you can really look at. So today quantum systems can solve certain problems. I'm not saying that you go for every problem to solve with quantum. Choose the problems wisely, such as quantum optimization. And using the QAOA, you can really look at the combinatorial problems more efficiently. Use the quantum simulation methods so that you can really take classical systems which are struggling, and you can use quantum simulation techniques to exponentially scale these areas, especially the traveling salesman, portfolio optimization, quantum chemistry for the simulating molecular interactions are possible, especially in the supply chain, real-time logistics, advanced material design. This can be a great advantage for optimizing the things to a great level. So just to summarize, these are some of the benefits what you need to be really aware. And we are just coming close to the entire talk, but wanted to give you a view that when you are trying to look from this entire standpoint, you need to understand what are the tools and frameworks we are able to leverage. My intent is only to expose you to the Qiskit, Circ, and some of the frameworks which are introduced through the Xanadu, so that you have an opportunity to build an approach of quantum classical integration, so that TensorFlow Quantum, Penny Lane, Qiskit machine learning frameworks can be leveraged to solve some of the critical problems. You can experiment using your current hardware also. And if you need some more intense, probably some of the quantum machines which are provisioned as part of the AWS or Google or Azure can be leveraged to an extent. I'm not saying that you have a great machinery. I mean, so you don't have 128 qubit you need to use. You can use even a 4 qubit machine or 8 qubit machine, looking into the cost dimension standpoint. So there are several challenges what you need to really look at integrating the quantum machine learning. Noise and errors in current quantum devices are very, very high, and you need to have a need for quantum error correction techniques. And there is today, as I said, hardware is always a challenge, and you need to start focusing on bridging the gap between the quantum researchers and the classical system developers. That the mode of thinking is not that if classical things are not solved, we need not, we should go with the quantum machine learning. No, you can combine them together, and that combination can play a very, very important role for the future. And that future is very, very advantageous because you see that potential advancements in the QML can really, really help you in this entire journey. So the role of advancement in the QML is very, very high. I want you to really focus on the full long-term vision, which can envision the machine learning system in the future world. And in the education curriculum also, when you're trying to look at, try to give as in many examples to the students, which can really help them and correlate with their thought process, indicating how the quantum driven future in AI can trigger. Enabling that kind of a literacy in the academia can play a very, very pivotal role. And it also helps in developing the interdisciplinary research in the quantum computing and machine learning. So some of these areas which you can interlink and take it back to your academic area and make it much more purpose driven. That is the intent I wanted to touch upon. And I just want to thank all of you for this particular opportunity given. I'm open for questions. And if there are any questions, I'll be glad to take it up and answer.
Yes, sir. There are some questions in the chat.
Sure. Let's utilize chat window to read through that. You want to read out, ma'am?
Yeah, yes, sir. I will read out. So can all classical machine learning algorithms be directly adapted to quantum computing, or any specific modifications are required?
I have one question. Can all classical machine learning algorithms be directly adapted to quantum? Now, we discussed about some of the critical examples, what you need to really look at. So once you encounter a limitation within the classical algorithms, then you can look at the opportunity to use some of these algorithms mentioned in the quantum area. So in the hybrid world, what you need to really look at is understand the limitations and the constraints of the classical algorithms. If that is encountered, then look at the possibility of dividing what need to be done with the classical algorithms, what need to be divided with the quantum algorithms. Say for instance, if your use case has an optimization issue, some of the optimizations can be still done with the classical algorithms with the limited data sets. But if the volume is constantly growing and your parameters are very, very high, then you divide the optimization as a responsibility for the quantum and rest of the things here. So you can choose the problem wisely, then it can really make a big difference.
So how can we develop hardware accelerators for QML computations on classical hardware?
A very interesting question, but you feel that it's really needed that you need to develop this hardware accelerators, or as you want to provide it as a kind of a software accelerators which can really play an important role. I don't know, but so if you typically look, you need to look from the simulation standpoint. My way of looking at it is when you are designing the accelerator, it is essential that you understand the computational challenge under which you're trying to operate using the quantum machine learning. The first thing is you need to look at high-dimensional linear algebra because QML simulations involve operations on larger matrices. It could be the Hamiltonian functions or quantum state vectors or the density matrices. Similarly, second important area what you need to really understand is about the quantum state representation, so that you can look at how the quantum states can grow exponentially with the number of qubits. And third is complex quantum algorithms like we witnessed about VQE, that is a variational quantum eigensolvers or quantum approximation optimization of algorithm or quantum kernel methods, where it requires high computational throughput. So when you look at it, that is a one area where you try to understand where actually the requirements are coming in for the simulation. The second area when you're trying to build and designing an accelerator is you need to look at the key components which are involved in the hardware accelerator of the QML. Especially, you may look from the specialized linear algebra units, which could be the matrix operations or the sparse matrices, or from the simulation angle, you may look at tensor operations or the compressed representations, or in the parallelism area also you can try to look at. So when you, and in the optimization solver, that is another space where the design accelerator is playing an important role. That is coming in the quantum inspired solvers or the radium based solvers. So these are some of the areas where the hardware element play important role because these are the dedicated units which are required to composed for enabling it. And the third important step is to develop QML hardware accelerator. That's where the designing the hardware architecture come in. Now, I'm not an expert in this domain to kill you or give you the information, but with my limited knowledge, I'll tell you that when you're trying to design the hardware architecture, you need to use this FPGAs, right? Field Programmable Gate Arrays or ASIC to develop specialized hardware for the QML tasks. So utilizing that, designing the hardware architecture, choose which one is more wiser in your nature and optimize the software hardware integration where you are trying to utilize some of the specific libraries. It could be the CUDA library or SYCL library or even the NEMO framework coming from the NVIDIA. And you leverage this existing accelerators and then you start benchmarking and optimizing it further. So it's a kind of a process so that you can really look into the overall current challenges in developing these things, because every QML hardware accelerators need to look from the exponential scaling standpoint, memory bottleneck standpoint, and the hardware cost it would incur. So it's a tough ask, but you need to look at some of the practical learnings. I would encourage you to review NVIDIA CU Quantum. It is a quantum circuit simulation on the NVIDIA GPUs. It's enabling an accelerated computation for the QML tasks, CU Quantum. The second thing which I want you to review is Google's TensorFlow Quantum, which we reviewed in this particular talk, because it is used to accelerate the hybrid quantum classical ML models. The third I want you to review is the AWS Bracket hybrid jobs. Basically, it's for the quantum computation for optimization of the QML tasks. These three things, when you review, you get a better understanding. It will help you to design the right accelerator for the hardware, what you are trying to look at. That in a nutshell, I can tell, but reviewing these three accelerators, which I mentioned, can help you to offer a direction and also inspiration to build that accelerator for the future.
Thank you, sir. So what are the primary advantages of quantum parallelism over classical parallelism?
This is pretty straightforward, I feel. You know that when you are trying to look from the parallelism standpoint, the advantages are very, very high. The exponential scaling is what we spoken about, right? That's one of the major advantage when you try to look from. So in a quantum system, when you're trying to look at a quantum processor with n qubits can represent 2 to the power of n states simultaneously due to the superposition what it is trying to talk about. So if you say 50 qubits, 2 power 50 states simultaneously, and you can imagine what is feasible for classical system and what is feasible for quantum system. And in the classical parallelism, what happens is you are using the multiple processors or multiple threads to divide the workload, and which is evaluating the state and coming back. But the level of parallelism which is provided in the quantum is exponential in nature. The second important advantage is superposition of states. In quantum parallelisms, we witness that superposition of states are immense. It can enable the parallel computation to be much, much faster. Take this example of the Grover search algorithm, where quantum computer can evaluate all entries in unsorted database simultaneously find the desired item simultaneously. But in the classical parallelism, even though you're trying to do that, it's limited by the hardware availability, and it is limited by the ability to scan through the pages to arrive at that particular search result. So quantum superposition can really eliminate the need for data partitioning. It can eliminate the need of reducing the overhead and enabling the true parallel computation, what you try to look at. The third advantage, what you see, is exploiting the quantum interference. So basically, in the quantum world, your ability to provide a concept of utilizing the constructive and destructive interference will help you to amplify the probability to arrive at the result. Shor's algorithm is a classic example which can determine the prime factorizations, which can leverage interference for efficiently finding out large number factors. While in the classical, you don't have that opportunity. So it really enables the convergence of the correct solutions compared to the classical brute force or heuristic methods. And last is you have a reduced hardware requirements for certain problems. So basically, a quantum system with 10 qubits can process 2 power 10, 1024 states in one operation, whereas classical system would require 1024 processes for the same tasks. You can understand the difference, the similar kind of a thing and the way you try to look at it. Last, a few other things which you may need to really look at is our high dimensionality and the quantum speed. All this plays a very, very important role in the parallelism when you're trying to look at. These are some of the advantages which I want to communicate.
Thank you, sir. All the questions are answered. Best QML for multimodal data, such as image and text pair with emotion recognition.
What kind of multimodal data you're trying to look at?
Image text pair with emotion recognition.
Any domain is also linked to it? I just want to understand, are there any kind of a domain? It's a healthcare data or is it a retail data? Because sometimes domains also plays a very important role. But if you're trying to look at from the basic QML under which you need to really operate on the image and the data, then you can really look at quantum machine learning. I just want to understand, it's basically text pair with emotion recognition. This is also another dimension which you're trying to add to your question, right?
So Facebook images like generalized data, they are asking.
Okay.
Social media.
And they are also asking for some of the image text. So I would say you should use quantum variational autoencoders. That would be the right thing which you can really look at, because emotion recognition for multimodal data, when you look at, it requires basically the features from different modalities And QML can really offer that advantages. And I strongly feel that quantum variational autoencoders could be much suitable for your need, because it can encode multimodal data into compact quantum states. And that will really allow you to compress your multimodal data into a unified latent space and capture a lot of complex dependencies. Oh, you can leverage these things. So second important model, probably you can experiment using the quantum convolutional neural networks. That again, because it has got an ability to process image data quantum mechanically, and it has got an ability to uh, develop the feature fusion for the multimodal tasks that can really bring that advantage. The third thing which you can really use is the quantum kernel methods. Quantum kernel methods are good because it can transform image and text features into high-dimensional quantum feature spaces. And when you are able to transform to the high-dimensional quantum feature spaces, you have an opportunity to define emotional recognition much more suitably. And that can help your models to be interpreting and identifying the pattern sets much more easy. And in the hybrid world, if you're trying to look at hybrid QML worlds, if you're trying to look at, you can look at the pipeline creation where you can create text processing, image processing, fusion layer, and classification layer. So you can have a quantum classifier which can help you to predict the emotions, while the rest of the things can be done by the classical layer. And Penny Lane would be the best, one of the best multimodal QML what you can leverage. What we're seeing, we leverage Scene, Qiskit, Penny Lane, and other methods, right? You can use Penny Lane QML. That's best.
Thank you, sir. Thank you so much, sir. On behalf of all the participants and organizing team, I extend my heartfelt gratitude to you for the enlightening session. You have provided a valuable insights on the integration of classical systems with the quantum computing and how it will be implemented using different platforms and frameworks. Sir. So thank you so much for your time and contribution for this FDP, sir. Thank you once again.
Thank you, and all the best wishes for the rest of the FTP. Thank you.
Thank you, sir.